In the world of computer science, sorting is a fundamental operation. We sort data all the time, putting things in order to make them easier to understand and work with. Imagine finding a word in a dictionary that's not in alphabetical order. It would be a nightmare. We have many clever algorithms for sorting, each with its own strengths and weaknesses. Some, like bubble sort, are easy to understand but can be slow for large data sets. Others, like merge sort, are faster but more complex. Today, we'll explore a unique algorithm called counting sort. What sets counting sort apart is its approach. It doesn't compare elements directly like most sorting algorithms. Instead, it leverages a clever counting technique to determine the sorted order. This unique characteristic makes it exceptionally efficient for specific scenarios. Let's dive into the details and discover how this intriguing algorithm works its magic. Counting sort is not your everyday sorting algorithm. It's a specialist, excelling in situations where the data has certain characteristics. Specifically, it shines when dealing with a small range of values. Imagine sorting the ages of students in a classroom. The ages will likely fall within a small range, say 5 to 10 years. Counting sort also loves whole numbers. It can even handle data that can be easily converted to integers like characters in a text. In these scenarios, counting sort can often outperform more general-purpose algorithms. However, it's not suitable for all situations. It struggles with large ranges of values, like sorting all the books in a library by publication year, or with data that can't be easily represented as integers like complex floating-point numbers. Why would we choose counting sort over other algorithms? It boils down to its efficiency and unique advantages. When the conditions are right, a small range and integers, counting sort is incredibly fast. It can sort data in linear time, which means the time it takes increases proportionally to the number of elements. More data, more time, but in a very manageable way. Counting sort also maintains the relative order of equal elements, so if two students have the same age, they'll appear in the sorted output in the same order they were in the input. Plus, the algorithm itself is relatively easy to understand and implement, making it a good choice for beginners. However, counting sort does have its limitations. It's a bit space-hungry, since it requires additional memory to store the count of each element, which can be a problem for large datasets. Its use is also restricted to specific data types and ranges. Despite these limitations, counting sort's speed and simplicity make it a valuable tool in a programmer's arsenal. Let's understand how counting sort works with a simple example. Imagine we have an unsorted array, 1, 4, 1, 2, 7, 5, 2. Our goal is to sort it in ascending order. First, we find the range of our data. The smallest is 1, and the largest is 7. So, we create an array of size 8, since that's 7 minus 1 plus 1, to store the count of each element. We iterate through the unsorted array, incrementing the count at the corresponding index in our counting array. For instance, since 2 appears twice, the index 2 in our counting array will store the value 2. Next, we modify our counting array to store cumulative counts. Each element will now represent the count of elements less than or equal to its index. This helps us determine the position of each element in the sorted output. Finally, we create a new array for our sorted output. We iterate through the original array in reverse. For each element, we look at its count in the cumulative count array. This count tells us its position in the sorted array. We place the element at that position and decrement the count in the cumulative array. By the end of this process, we have a sorted array, 1, 1, 2, 2, 4, 5, 7. Counting sort's unique characteristics make it suitable for various real-world applications. For example, it can efficiently sort characters in a string, which is a common task in text processing. Analyzing exam scores, which typically fall within a limited range, is another ideal use case. And in bioinformatics, counting sort is used to sort DNA sequences represented by a limited alphabet of nucleotides. However, its limitations are crucial to remember. For datasets with a vast range of values, the space required for the counting array can become, well, pretty prohibitive. It's also not directly applicable to data that can't be easily represented as integers like floating-point numbers. In conclusion, counting sort stands out as a specialized sorting algorithm with exceptional speed and efficiency for specific scenarios. While its limitations restrict its use to certain data types and ranges, its clever design and unique approach highlight the ingenuity of algorithms in solving computational problems.